right, hello, welcome to this week's Math 2414 weekly review. So I know it's been a couple weeks, but this week we're going to go ahead and cover section 7.5, which is integration strategies, and section 7.8, which is improper integrals. So let's go ahead and get started. All right, so let's go ahead and pull up. And so now let's go ahead and think about what we have for our strategies. So when we think of our strategies for integration, this is essentially compiling everything we've done within Chapter 7, as well as a little bit of what we did at the end of 2413. So let's go ahead and think about what we have. We have just some of our basic rules, such as like power rule, and then like natural log, trig, exponentials, things like that. Those are all pretty basic stuff that we've kind of covered extensively throughout this course and a little bit in 2413 as well. And then we also have some of our newer things that we've covered that were new for this semester. So for example, we have some other trigs. So for example, like integrating stuff such as secant and tangent, like those are like new ones that we've done. Inverse trig is pretty new as well. So like we just have we've learned a bunch of rules, and now there is a table in your textbook with a bunch of with pretty much anything that we have that can just be plugged into just a normal rule. So now we have to think about how we can kind of combine everything, because not only do we have these, but we also have different integration techniques such as U sub, trig sub, integration by parts. So let's see how we can kind of combine all of this information and put this into something that's actually pretty easy to learn. So there's actually kind of like a basic thought process that we can use to kind of think of this. So this is like a thought process that you can use for pretty much any integral. So step one will go ahead and be simplify the integrand. So for example, we can kind of take into what we have in our integral and see if we can kind of go ahead and simplify that a little bit to make it to where it's something that's a bit easier to look at and digest. So there's a couple ways we can usually do this. We can do that algebraically. And like that's, for example, that is something to where we have something along the lines of, let's say we have x cubed plus 3x squared plus 3x plus 1 over x plus 1. That on paper looks like a not completely fun integral, but if you actually go ahead and if you know the factors off the top of your head, or if you do your long division, that actually simplifies out pretty easily to just x squared plus 2x plus 1, and that's just a basic power rule. Or you can have something like with trig. Or you can kind of simplify using different trig identities. So for example, if we have something along the lines of secant x times sine of x, that initially doesn't look like the easiest integral to solve, but then we can actually turn that into sine over cosine, which is just tangent of x, and we have a formula for that. We can just plug and chug, boom, we're done. So going off of that, our step 2 would be to go ahead and look for an obvious solution. So usually that's just something to where we just have like an easy rule, like just use like a direct rule. Like if we can see it and say, like, for example, in the previous ones, how we have our tangent, like how we can just substitute in the integral for tangent, or up here we just have basic power rule. Anything like that's where you can just look at a formula chart and be like, oh, okay, that's what we're going to do. Or you can go ahead and see if you can do just like a quick and easy U sub. But let's say that we have gone through steps 1 and 2 and we still don't necessarily have a bunch of stuff that we can really work with. That brings us to our step 3. And this is essentially where you want to match the form to the technique, to our integration technique. So there's a few different examples of this. So for example, if you see trig functions, particularly if there are in these pairs, such as like sine and cosine together, tangent and secant, or cotangent and cosecant, if you see those together, that is a pretty that's a pretty big hint that you're going to probably be doing some sort of U sub, which is what we did in, I believe, section 7.2. So where if we had something like tangent to the 5th times secant cubed, you went ahead and just factored out things to get everything in form of tangent or get that in the form of secant. Like, I'm not going to really try to solve that right now, but where you can kind of combine everything and then just kind of break that down to where you could be like, oh, u is secant of x or u is tangent of x, and just move on from there. The next strategy that we have is, the next way we can match this is if we have rational fractions. That is, if we see that, we know that we probably need to do some sort of partial fractions. So, for example, like if we see something like this, 3 over x squared plus 2x plus 1, we know that we can't really do anything in that format right now. So what we could do is we can just go ahead and just easily convert that to 3 over x plus 1 squared, or I guess you could do partial fractions, or in this example, you could even just go back and do a U sub. Whatever works for you. This whole lesson is essentially about how to go ahead and solve for things like this. So, like for example, yeah, you can either do partial fractions, or like I said, in some cases, once you kind of clean that up, U sub. The next way we can go ahead and, the next strategy we can use would be integration by parts. Now, you can do integration by parts for pretty much any integral. It's just about whether or not how easy it's going to be. So typically, if you use integration by parts, you kind of want to use it either, you want to combine an algebraic with the transcendental. And of course, by transcendental, as a review, that pretty much means either a trig, exponential, or a log. So for example, x times natural log of x is a perfect example of when to use this. But like, let's say, but if you had like some other one, like let's say maybe we had e to the x cosine of x, that wouldn't necessarily be a good way to do it, because you would make it into a situation where you're going around in circles the whole time. Since so yeah, when you're doing transcendentals, that's always a good thing to keep out with. Logs aren't as bad to combine because those will eventually simplify out to transcendentals, but I mean to algebraic functions, but exponentials and trigs will not. So then of course we have radicals. Now there's actually two different ways you can work with this. If you have some sort of an x squared and some sort of an a squared in there, that you are going to do a trig sub. So for example, if we have x cubed over square root of x squared plus 9, then you know theta is 3 tangent of, you know that x is 3 tangent of theta. But there's another one, we haven't really covered this one as much, but let's say you have some sort of radical, doesn't matter what power, and you have some sort of function, especially if it's a linear, but you can do this for any function under a radical. You can usually have to do some sort of u sub, is kind of a big hint. In some cases, you can either just directly say that this whole function is the u sub. In other cases, you can say it's just the part under the radicals, the u sub. It just kind of depends on a case-by-case basis. But for like an example of this, since I know we don't see these as often, would be something like cosine of the square root of x dx. And lastly, I would also say if you have like some sort of like a weird quadratic, that's just like the best way I can put it, you can complete the square. And then you can, from there, you can either do u sub, do trig sub, whatever you need to do. Like an example would be like if you had something like, if you're integrating just the square root of like x squared plus 4x minus 11, where you can't really do anything with that, you could go ahead and see if you can maybe try to complete the square and see if that gets you anything. It may not, but you can always try it. I know there's some examples like this, I believe, in the section that covered trig sub. They do a bunch of examples. They have a few examples in the back of the book for that. So now let's think about what happens if we are still not there. So for step 4 is for if you still are not there, just kind of a mix of this is either just try again. Like you may either have to completely try again or kind of see if there's a different way you can just work further. So what I mean by this is there's like a few different ways that you can do this. You can either go back, since most of these strategies come down to either integration by parts or some sort of substitution. You can either try to find an alternate substitution. So for example, you try u sub, it didn't work. What if you tried either expanding or narrowing what you did in that u sub? You can find an alternate integration by parts. So for that, let's say you have 3 different functions, you can try combining them into, like, so let's say you have something along the lines of like x, sine of x, cosine of x. You may have to go ahead and work with those and rearrange those in try different groupings. Like you could try x sine of x, you could either just group these two or group these two or group these two. You may have to play with it and see what will get you the answer. Another one thing that you can do is try to manipulate the integrand again. So go back to step 1 and see if there's something else you can try. So I remember whenever we did our proof, whenever we went in class, whenever they went over the proof for how to solve the integral for secant, they showed how you kind of had to do that weird, like you have to do some weird substitutions, weird manipulations to be like, oh, what if I just multiplied secant plus tangent over secant plus tangent? Like you may have to play around with things like that. Another thing that you can do is maybe, if you can, maybe think back to previous examples. And see if maybe that'll help you and be like, oh, we did a problem similar to this, or hey, I got to this point in a different problem. What did I go do when I did that one? And probably the most one that you're going to come across is the most important one that you'll come across is the most is combine different methods. Like you may have to do a trig sub and an integration by parts in the same one. So I'm going to go ahead. Oh yeah, and then from here, you can keep trying and see what you get, but it is important to know that you may have some functions that they're just never going to integrate. So if it's a test, they probably will not give you something like that on a test. Like I doubt they will give you something to where it's going to be, oh, you just can't integrate it. But there are some functions out there that just don't integrate. So just kind of keep that in the back of your mind, but that's usually not something that they will test you over or give you a ton of homework problems on. So it's important to know, but it's not that important for this course. So I want to try a couple of examples and kind of show how we can work through this. So for our first example, we want to integrate e to the arctangent of y over 1 plus y squared dy. All right, so I usually like to go ahead and just kind of do like a quick little like survey and be like, okay, what do we have? We see we have a 1 plus y squared. That could be something. We have an arctangent of y. That could be something. And of course, we have an exponential to another function. That could be something. So let's go ahead and think back to step 1, which is manipulate the function. So there's really only one way we could do this. And we could try to maybe separate out the numerator and the denominator. E to the arctangent of y times 1 over 1 plus y squared dy. So now let's go to step 2, look for an obvious solution. So if we think back to all of the formulas we've learned, there is an obvious solution to this one. We see that we have an arctangent of y right here, and we also know that the derivative of arctangent is going to be, if we take the derivative of 1 over arctangent of x, it'd be 1 plus x squared. Well, we have an arctangent of y in a 1 over 1 plus y squared. So that's a pretty big clue. That's going to be a u sub. So therefore, we can let u be arctangent of y. du is 1 over 1 plus y squared dy. Therefore, we are now at e to the u du. Integrate, we get e to the u plus c, which will then go over to e to the arctangent of y plus c. So yeah, that one's actually not that bad once you actually kind of get to play with it a little bit. So now let's try another example. In this one, we are integrating from 1 plus square root of x all to the 8 dx. All right, so now let's think about what we have here. Step 1 we have would be to manipulate the function, but really the only good thing we could do would be to expand this. The only thing is that we are going up to the power of 8, so I would not recommend trying to expand anything higher than like 3, maybe 4 if it's something really, really simple. So because of that, I would actually not expand this one. You could expand it and get a basic power rule, but you're also more likely to end up in a situation where you just get a bunch of really, really messy scratch work and things are going to get just kind of confusing, and you're going to there's going to be errors, just easy math mistakes made in there. And if we look at this, we also don't have like a pretty basic solution that we can use like the last one. We don't have anything that just comes off the rule book or that comes off of like our formula sheet or anything. So now we have to go to step 3 and then see if we can match our form to something else. So if we think back, it's not trig, it's not a rational function. Not a great situation for integration by parts, but we do have a radical. And this is one of those cases to where you would try to do a u sub for a radical. So I am actually going to go ahead and show you guys how I did this, like my full thought process when I did this problem. That way it can kind of show you how to work through these. So when I first went through this problem, I said, So when I first did this problem, I said, okay, we are going to let u just be the radical. Let u be square root of x, and then du would be 1 over 2 square root of x dx. So if we do this, we are going to get, and then from here we also have, so we have a situation for our u, and if we solve for our dx, we are getting dx is equal to 2 square root of x du. So if we plug everything in, we get our integral of 1 plus u to the 8th times 2 square root of x du. We still have that square root of x, but we can just plug in a u for that. We get 1 plus u to the 8th times 2u du. So the thing is right here is this still isn't a great format for us to try to go ahead and integrate. We could do an integration by parts, but that could get kind of messy. Instead, let's go ahead and just try to go ahead, because at this point, like you just want to, it can get kind of messy whenever you have like, okay, now we went from x to u, and now we have to go from u to like u and v, but we already have a u, so f and g, it may get really, really messy. If you want to try it that way, go ahead, but instead, let's look at another way we can do this. Since we've cleared our step 3, but that didn't really help us much. What we can do is we can actually go ahead and go back and try again and find a different substitution. So let's try this again. This time we're going to let u be the square root. U is going to be 1 plus the square root of x. And then therefore du is still going to be 1 over 2 square root of x dx. And of course, if we go back, we still get dx is equal to 2 square root of x du. So now let's go ahead and set up this integral again. So we have u is 1 plus square root of x, so u to the 8 times 2 square root of x du. Now we have to look at this square root of x. So up here, what we can actually do is, since we have our u already established, we can actually play with that a little bit. If we know that u equals 1 plus square root of x, we can actually still solve for square root of x and say that square root of x is equal to u minus 1. We still have an x in term, we still have everything in terms of u on one side, but now we can take care of this x. That's square root of x, so we can now have, I'm going to go and pull that 2 outside of the pull the 2 out. So now we get u to the 8th times square root of x, which is now u minus 1 du. Now we're in a good format to where we can play with this and actually integrate, because now we can get 2 times the integral of u to the 9th minus u to the 8th, and now we're just at a basic power rule. We get 2 times u to the 10th over 10 minus u to the 9th over 9 plus d, u to the 10th over 5 minus 2u to the 9th over 9. And then we just plug in our u, and then we are left with 1 plus square root of x to the 10th over 5 minus 2 times 1 plus square root of x to the 9th over 9 plus d as our final answer. So that kind of shows you how you may have to kind of play with this a couple different times until you finally get an answer. And then I have one more that I'm going to go ahead and do for this section. So for this one, we are going to integrate 1 plus sine of x over 1 plus cosine of x. So if we look at this, if we go through our little steps, our first step would be to try to manipulate the function. So on paper, we could try to split up this function to get us 1 over 1 plus cosine of x plus sine over 1 plus cosine of x. The only thing is that still doesn't really get us in like a great form to do anything. You could still maybe try it, but it's not like a super ideal form. You may be able to get something with it, but I personally may not try it. You can try that method at home and if you want, but what I thought of was, what if we tried to manipulate this function by multiplying it times 1 minus cosine of x times 1 minus cosine of x. That way we can take care of the bottom and then try to kind of split this up a little bit more. So let me show you what I mean. If we take 1 plus sine of x and 1 plus cosine of x times 1 minus cosine of x over 1 minus cosine of x. If we do this, we're going to get 1 plus sine of x minus cosine of x minus sine of x times cosine of x, all over 1 minus cosine squared of x. And from here, we're actually in a good form to do our Pythagorean identity, since we know that 1 minus cosine squared of x is actually going to just be sine squared of x. So from here, we can actually now split this up into 4 different fractions and integrate those. So we can now get one over sine squared plus sine over sine squared minus cosine over sine squared minus sine cosine over sine squared. So now we can go ahead and once again continue to kind of simplify this some more. So if we take 1 over, so we know that 1 over sine of x is equal to cosecant. So from here we get cosecant squared of x plus sine over sine squared is 1 over sine, so cosecant of x. We now have a cosine over sine squared. This can split up into cosine over sine times 1 over sine to get us cosecant times cotangent. And then, of course, over here, we get cosine over sine. When we simplify that, which is once again cotangent. Now at this point, you can go ahead, you can go look at the formula chart in your book, and you can actually now see that all 4 of these pieces all have a formula associated with them. So just for time's sake, I'm just going to go ahead and write out the final answer. We have cosecant squared would go to negative cotangent of x. Cosecant would go to negative natural log of the absolute value of cosecant minus cotangent. This minus cosecant cotangent would go to just a positive cosecant. And this minus cotangent would go to a plus natural log of sine. So therefore, our final answer, if we kind of rearrange this, would be cosecant x plus the natural log of the absolute value of sine of x minus cotangent of x minus the natural log of cosecant minus cotangent plus c. So now we're going to go ahead and move on to our second section for today. This one, so this section is going to be over improper integrals. So in short, improper integrals essentially means if you have an integral which either has an infinite bound or infinite discontinuity. So there's actually 2 main types of improper integrals. when we're talking about this. We have our type 1, and these have to deal with infinite bounds. Now, there's 3 main cases whenever we're talking about this. In case 1, we have an integral that is going from some number a to infinity. It's just the integral of any f of x dx. So whenever we have that case, what we actually have to do is we have to rewrite this as a limit. Means to have the limit as t approaches infinity from a to t of f of x. Type 2 is very similar to type 1, except instead your bounds are from negative infinity to some number b. But you still treat it the same way, to where you substitute that infinity or that negative infinity in for t. And we now have our limit as t goes to negative infinity from t to b of f of x dx. Oh yeah, and both of these are continuous on their intervals. We will deal with that later on, if they're not continuous. And of course, we have our case 3, which is whenever we actually go from negative infinity to infinity. And whenever we have that situation, we have to actually break this up into two separate integrals. When we do this, we can pick any just arbitrary a that we want to. We can say, like, a can be anything, but we can use it to separate this out into 2 limits. We can say the limit as t approaches negative infinity from t to a of f of x plus our limit as t goes to positive infinity from a to t of f of x dx. So this now now that we have our type 1 defined in the 3 cases, that brings us into a discussion of this concept of convergence and divergence. So, in short, being convergent means that your limit exists. So when you take that limit, you get some. So whenever you take the limit of any of these cases, like right here, you will get some finite number. And if you have something that is divergent, that means your limit does not exist or goes to infinity. Go ahead and definitely, keep those terms in mind, because these actually will come back at the very end of the semester whenever we start talking about series. So whenever we're thinking of convergence and divergence, we essentially are trying to figure out, hey, if we take the area under this curve, is it a finite number or is it an infinite number? So for cases 1 and 2, if if limit exists, it's convergent. Case 3 is a little different. For this, both limits must converge for the whole thing to be converged. If one of those diverges, then the entirety can't converge. So for example, if this part converged and this part diverged, then this whole thing would be divergent, because essentially that first part could be equal to 1, but if your second part is equal to infinity, 1 plus infinity is infinity. So I'm going to go ahead and do a couple of examples on like how we kind of do improper integrals. So for both of these, we want to figure out if they are convergent, and if they are convergent, and what number they do converge to if they are convergent. So for our first one, we are going to go from 1 to infinity of 1 over square root of x. All right, so of course we can rewrite this. Whenever I have radicals, I tend to like to just rewrite them as fractions, just because I feel like that makes it easier for power rule. So now if we go ahead, so now we have this, but now we must go ahead and split this up into, or not really split it up, but rewrite it. So we need to actually go ahead and rewrite this to take care of that infinity. So we're going to say that our limit as t approaches infinity of 1 to t x to the 1/2 dx. So now we're in a spot to where we can actually go ahead and integrate this. So x to the -1/2, that's a pretty easy integral. That's just going to be add 1, you're going to get 1/2, and then take care of the coefficient, which is 2. And then of course our plus c. But since we're doing definite integrals, we don't have to worry about that as much. And of course we know that we are going from 1 to t, and are taking the limit as t goes to infinity. So if we go ahead and plug this in, we are going to get 2 square root of t minus 2 square root of 1. And the thing is, if we take our limit as t approaches infinity, if we're going to get infinity minus 2, which is infinity. Therefore, this is going to be divergent. And just a general rule, if you have let me pull it up, just double check so I don't tell you the wrong number. If you're taking, yep, there we go. Just as a general rule of thumb, and this will also come back later on in the semester when we do series, if you have the form 1 over x to the n and you're going up to infinity, if n is greater than 1, it'll automatically converge. If n is less than or equal to 1, it will diverge. So just a cool little fun fact that will come back into play later on. So now let's go ahead and do another example for this. In this example, we are going from 2 to infinity of 9 over 1 minus 3x to the 4th dx. So, of course, our first step needs to be to go ahead and rewrite this in terms of a limit. All right, so now that you've taken care of the infinity, we can go ahead and try to integrate. So right here, I would not expand this. You could if you wanted to, but that would actually be a little bit harder to solve, because what we can do is, since we have a power of 1 in the bottom, right, since we have a linear right here and a constant on top, we can just do a simple u sub. So we can go ahead and say that u is equal to 1 minus 3x, du is equal to negative 3 dx. So we now have, so if we 2 are an indefinite, we can go ahead and get negative 3 over u to the 4th du. That will get us to negative 3 u to the negative 3rd times negative 1/3. That will cancel, so therefore we get u to the negative 1/3, which is 1 over 1 minus 3x cubed, plus c is our integral. But of course, we still need to remember we have our bounds from 2 to t. So now let's go ahead and plug that in. So we have our limit as t goes to infinity of, we have 1 over 1 minus 3t cubed minus 1 over 1 minus 3 times 2 cubed as well. So if we go ahead and evaluate this, we can see that we get approximately 1 over negative infinity right here, minus 1 over negative 5 cubed. That 1 over infinity, that limit of that is going to actually go down to 0, minus 1 over okay. Negative 5 cubed, so therefore we are going to get 1 over 125. So now that actually brings us, so now we've done a couple examples for type 1. Let's talk a little bit about type 2. And this is essentially whenever we have to deal with discontinuities, in particular infinite discontinuities. So once again, we have 3 main cases. we have case 1, and this is whenever our interval is continuous at A but not continuous at B. So we have a curved bracket at B. So if we have an integral going from A to B, and we know that the function is not continuous at B and has then what we have to do is we rewrite this as a limit as t approaches b from the negative side of our integral from a to t f of x. Case 2 is whenever our interval is not continuous at A, but is continuous at B. And once again, we're integrating from A to B. In this case, we set our limit is going to be when t approaches A from the positive of t to B f of x dx. And lastly, case 3 is going to be whenever we have A is less than C, which is less than B, and f of x has a discontinuity at C, but is continuous at A and B. Kind of a lot of buildup. Essentially, if we are trying to integrate from A to B and we have a discontinuity in the middle of that interval, what we do is we actually have to break this up into 2 separate integrals, similar to what we did in type 1. It's where we have our limit as t approaches A from the positive, approaches C from the negative from A to C, and then then once again we have our second limit where t approaches C from the positive from C to B. And our convergence and divergence rules are the same here. Cases 1 and 2, if the limits converge, then they're convergent at that point. If for case 3, both of those limits have to converge for the full integral to be convergent. So let's go ahead and do a couple more examples. All right, so for this first example, we are going to integrate from -5 to 1 of 1 over 10 plus 2x. So our first step would be to go ahead and rewrite this in terms of our limit. So we are taking our limit as t approaches -5 from the positive side from t to 1 of 1 over 10 plus 2x dx. All right, so now that we are at this point, we can go ahead and integrate. If we look at this, we have a linear on the bottom, constant on top, assigned for a u sub, so we can let u be 10 plus 2x. du is 2 dx. So therefore, we are going to get 1/2 times du over u, natural log of u, So therefore, our final integral would be 1/2 times the natural log of the absolute value of 10 plus 2x plus c. And then now we have to go ahead and look at this with our, then we go ahead and plug in our bounds. It's where we get the limit as t approaches -5 from the positive of 1/2 times the natural log of 10 plus 2 times 1 minus 1/2 times the natural log of 10 plus 2t. So if we look at this, we get just 1/2 natural log of 12 for the first part. The second part, now we have to look at this. If we're saying that we're approaching -5 from the positive, that's essentially like we are plugging in -4.999 and so on and so forth. So if we do that, we are getting -1/2 natural log of 10 plus 2 times -4.999. So therefore, that would be the natural log of just over 0, approximately. So if we do that, we're getting infinity, right? That would go down. The natural log of 0 is approaching -infinity. So therefore, we get 1/2 natural log of 12 plus infinity. Since we have that infinity in there, we know that it is going to be divergent. All right. All right, let's try another one. In this one, we're going from 0 to 4 over x squared minus 9 dx. All right, so our first thing we need to think about is, first of all, we need to check to see if we have any discontinuities, which we do, since we know that x squared minus 9 is x plus 3, x minus 3, therefore we know that x cannot equal 3 or cannot equal plus or minus 3. So therefore we know we have that discontinuity at 3, so we need to go ahead and break this up into 2 different limits. So now we have our limit as t approaches 3 from the negative of 0 to t of x over x squared minus 9 dx plus our limit as t approaches 3 from the positive from t to 4 of x over x squared minus 9. So now let's go ahead and just look at one part of this, since essentially if one of these is divergent, the whole thing's divergent. So if we do the first one and it diverges, we can honestly just stop. If it converges, then we need to go check the other one. So let's go ahead and just look at this part for right here. right here, we can go ahead and say that u is 2x u is x squared minus 9, therefore du is 2x dx. So therefore we get our limit as t approaches 3 to the negative. Actually, we don't need to worry about that. We're just doing indefinites when we do this. So therefore we are getting the integral of 1/2 du over u. Therefore, we get 1/2 natural log of the absolute value of x squared minus 9 plus c. Then, of course, we plug in our limits, our bounds. So we have our limit as t approaches 3 from the positive. I mean 3 from the negative, of 1/2 natural log of t squared minus 9 minus 1/2 natural log of the absolute value of 0 minus 9. All right, so now let's go ahead and look and see what we have here. If we take this natural log of what is approaching 0, so what we can do is we can also just say we're going to let this be equal to, let's say, a natural log as limit as a approaches 0 from the positive. Yeah, just as a approaches 0 in general. Yeah. That's going to be equal to negative infinity minus 1/2 natural log of 9. Therefore, it's going to be divergent. Therefore, the whole thing is going to diverge because that part diverges. All right. So I actually have just one more example for today. All right. So in this example, we are going to go from 1 to 2 of 4x over cubed root of x squared minus 4 dx. So of course we need to see if we have any discontinuities, and if looking at this we can see that we're going to have 1 at 4. So 1 at 2 So therefore we're going to have to go ahead and rewrite this as our limit as t approaches 2 from the negative of 1 to t of 4x over the cubed root of x squared minus 4. All right, so now once again we can do a pretty simple u sub u is equal to x squared minus 4, du is 2x dx. So now we have a 2 out there coming from the 4, so we can now have u to the negative 1/3 du which will get us u to the 2/3 times 3/2 times 2. Those 2's will cancel out. So therefore, we're going to get 3u to the 2/3 plus c. And then therefore, we get 3 to the x squared minus 4 to the 2/3 plus c. Now, of course, we need to go ahead and take our bounds, going from 1 to t. So we now have our limit as t approaches 2 from the negative of 3 times t squared minus 4 to the 2/3 minus 3 times 1 minus 4 to the 2/3. All right, so now if we look at this, if we take our limit as t approaches 2, that's going to get us approximately 0 and for this part. If we take our limit, we're going to essentially get 0 minus 3 times negative 3 to the 2/3. So therefore, we get negative 3 times negative 3 to the 2/3. And we can simplify that just a little more to get us negative 3. So therefore, we can say that it is convergent to negative 3 to the 5/3. All right, and that is all I have for today. I hope everyone is safe right now. Yeah, good luck on everything else.